Hello, everyone. My name's Mike Neal. It's my pleasure to tell you a little bit about modeling developmental data, particularly on Markov or simplex models in this case. So, as an overview, I'll talk a bit about Markov models in general and a bit about Markov models in genetics and some neat developments by Connor Dolan and colleagues in order to show more complex developmental processes such as niche selection, whether we can detect those with longitudinal data collected from twins or other pairs of relatives. And very finally, I'll mention briefly the possibilities of adding genomics, polygenic scores, etc., to this type of model. But I imagine that we will teach more of that in years to come. So first of all, nomenclature, there's a whole lot of different names for various types of models that simply say that time 2 is some function of time 1 plus some additional residual variance. And in this path diagram, time 1's variance is shown as R1 in red letters. The regression of time 2 on time 1 is B1. And time 2 will then have some leftover variance specific to itself called R2 in red letters in this diagram. It's an empirical question that is readily answered by likelihood ratio test, whether or not B1, B2, and B3 are equal, or whether R2, R3, and R4 are equal. Typically, we don't ask whether R1 is equal to the other R components, other R parameters in this model, because R1 is subsuming all prior time variation and is expected to be, if the system had got to some kind of stability, that essentially B1 squared plus R2 gives us the total variance at time 2. And we'll note that a good deal of that variance might come from the term B1 squared times R1 by path analysis being the contribution of time 1 variation to variation at time 2. So this is a very simple and elegant model, and it can prove quite useful, and it can be interesting to decide whether there seem to be particular time periods, times when there is a burst of new variation. For example, if R3 was larger than the others, it would suggest that something developmentally special is happening around that time. There are, of course, limitations to this model, as there are limitations to every single model that we ever use. One of the sort of questions is, okay, what does it do if there's measurement error? It doesn't make a great deal of sense to transmit measurement error through the regression path B1 to time 2. If it's strictly measurement error, it will be strictly time and individual specific. If it's random error uncorrelated with everything else. So it would make sense to modify the model a little bit to allow for transmission at, say, the latent level of these variables rather than the observed, i.e. measured levels of these variables. So we can tack on latent variables to each of these measures and note some measurement error as well. And that leads to this next diagram, which in terms of the values of the path coefficients looks terribly complicated, but it really isn't. And it is, in fact, equivalent to the prior model once we put in the constraints. That is to say, we're constraining the total variance at time 1 to still equal R1, but that instead here we're estimating an R1 star, and the R1 star is actually residual measurement error. So what we have measured in the boxes, the squares at the top, contains both a regression on the true score. These are written as RT1, RT2 in the circles below. So it's a regression on their true latent score, in addition to some estimated from other quantities amount of residual error R1, R2, R3, and R4. And ideally, to get these R1 star, etc., estimates of reliability for an occasion, I think it's best to use very short time frame test retest data. The ideal experiment, of course, would be give someone the test, give them a brainwash so that they've completely forgotten their answers from the test that they just took. Make it a short-term brainwash, you know, just from the beginning of the test to the end of it. You don't want them to forget everything. But you, if you had then these two consecutive measurements that didn't involve any interference between the two measurements, you could have yourself a good estimate of test-retest correlation that's almost instantaneous. And one minus that would be a reasonable estimate for the R1, R2 star parameters at the top of the diagram. Okay, so and it would, be quite possible to do that in a statistically valid fashion by including in a separate group the test-retest data and estimating the test-retest reliability of those data. What I recommend against is using something like Cronbach's alpha or omega statistics that measure internal consistency, which is also sometimes called test reliability. But these measures of internal consistency don't particularly pertain to how precisely a test-retest correlation might be of a measure. So you could have a test with terrible internal reliability, but actually extremely good test-retest reliability if you just score people by the alphabetic number of the first letter of their last name and add their birth date in days since 2000, for example, and you would get pretty much exactly the same number, but there would be no internal consistency at all for that measure. And yet it could be perfectly reliable over time. So I did want to make that distinction clear. You will probably come across the so-called hidden Markov models, and what we just looked at was a variety of a hidden Markov model, but it was specified in a structural equation modeling context. More typically, the applications of hidden Markov models are fairly widespread and use time series data of observed measures. This example hidden Markov model is based upon hidden factors as to whether or not it's sunny or raining. That is, we are trying to infer whether or not the weather is rainy or sunny based upon somebody's activities and knowing the probabilities that they will engage in those activities given the weather. So this particular hidden Markov model here is saying that if it's rainy, I've got a 10% chance of going for a walk, 40% chance of going shopping, and 50% chance of staying home and cleaning. Whereas if it's sunny, I would have a 60% chance of going for a walk, 30% chance of going shopping, and 10% chance of cleaning. And it's possible to aggregate data over multiple occasions in order to estimate the probabilities that any particular day would be rainy or sunny, just given this sequence of time series of walking, shopping, and cleaning behaviors. The mathematics of this isn't necessarily relevant, but it is close enough that I think it warrants consideration. Typically, the way that this type of model works is by calculating all the possibilities of outcomes, and then just figuring out, okay, which particular outcomes are more likely over time. So here we would be looking at whether it turned out to be more likely to be rainy or sunny, depending upon the sequence of activities. There's a Viterbi algorithm that turns out to be particularly good at making calculations like that efficient. But again, that's not the realm of Markov modeling that we're dealing with here, where we're dealing with a structural equation model, and we are allowing for error of measurement in particular. Methods for analyzing very long time series exist, and in many cases, we're looking at multivariate data collected on an individual many dozens, hundreds, or even thousands of times, and use those data to fit particular structural equation type models. And OpenMX has facilities for making such estimation efficient. It has fully developed state space modeling capabilities where you can program dynamical systems models that are essentially of the form of saying that the change in X from time 1 to time 2 follows this particular functional form. If that's the case, what does the rest of the series look like? And do the data that I have collected seem to indicate good fit to particular state space models? Okay, next up, thinking a bit about estimating these hidden Markov models. It comes very close to the distinction between multi-group and multi-level modeling, and we can discuss those briefly here too. If we think about data collected from multiple groups, and they're shown not really distinguished in any sense in the left-hand figure here, with a measure X on the X-axis and Y on the Y-axis, and we just ignore the groups, we can estimate a single XY regression. We can also estimate the variances and the means of the variables X and Y. If we start taking group membership into account, as in the middle figure, we could simply not estimate a regression at all and just separately estimate means and variances for each of the groups. This would be a variety of variance components model. Last, we could also estimate regressions across these various different groups. We could estimate one regression parameter and have the same slope for everyone, and this is what we call a random intercept model. And it is different from a model that has both random intercepts and random slopes. In the last case there, you would expect the yellow lines in the right-hand figure to have different angles according to the regression within each of those particular groups. And that brings me to considering the alternative approaches to dealing with random intercepts and slopes in structural equation modeling. One is simply to use a very heavy-duty multi-group approach. If you've got 100 different schools and you've got kids measured in each of them, it may seem rather cumbersome to put this into a multi-group model with 100 different MX models. But in practice, the overhead for doing that isn't very high, and particularly by being embedded in a programming language environment such as R, it becomes very simple to assemble extremely large MX models containing many, many different groups and to estimate separate means, variances, and covariances for every group. And as an approach to multi-level modeling, that is fairly good. It can run into difficulties if the sample sizes get particularly small in certain groups, then those estimates might not be very precise or might not be available at all. A second approach to tackling multiple groups in this sense would be a multi-level perspective, and saying that that these characteristics of the groups, their different means, their different intercepts, and their different regressions, that those statistics, when we look at them across all these different groups, may come from a population with a given distribution of means, regressions, and variances, for example. And it's possible to characterize those differences between the groups in terms of say, a normal distribution with a mean effect, a mean parameter value for all of the groups, and some variance in the parameter values across the groups. And this second multi-level approach is very efficient because you're simply adding two parameters to a model catering for a very wide variety potentially of different groups. So Occam's razor might encourage us for not having multiplied entities, or in this case, parameters, without necessity. But the multi-level approach, of course, is making additional assumptions about the distribution of those statistics. And if those assumptions are wrong, then one can expect bias in other parts of the model. So back to our AR1 model with random intercepts. We're seeing that the latent RT1, RT2, etc. variables here are now not merely influencing one, has an influence to the next one in time, but they're also jointly influenced by an intercept factor shown at the bottom with a variance of 1. That variance is actually a parameter that can be estimated so that we can estimate how much variation there is in the intercepts essentially here. And what this effectively does to the model is make it a model for individuals varying around their own mean, as opposed to all individuals varying around the population mean. So this rather nifty addition of a common factor behind the variance components here, and behind what is essentially Markov factors, really puts the model into a different mathematical framework. And typically such a model is likely to show improvement in fit. So as I was saying, it's modeling individual change around their own mean rather than the population mean. It's very cheap, only adding one parameter. It accounts for common influences on each time point, that is a dose of variance that they all get. But this approach doesn't automatically add random slopes. So, well, if we take these, what are actually quite popular models for the analysis of time series in non-behavior genetic disciplines, and we start to consider what do they look like genetically, the late great Professor Lyndon Eaves shared his thoughts on this type of modeling in an exceptional paper in a special issue of Behavior Genetics in 1986. And this model was, I think, the first presentation of a Markov model for longitudinal data collected from pairs of relatives. He divides variation into environmental and genetic, E and G. The occasions run down the diagram from E0, P0, and G0, forward to in time to P1, P2, ... to PM, etc. The model is featuring transmission through these eta paths from environments at one occasion to the environment at the next occasion. It's also transmitting genetic variants from one occasion to the next through these gamma paths. And furthermore, has phenotype to phenotype transmission with these P transmission parameters. I suppose he chose P instead of pi, not to be confusing with geometry. But it turns out that these three different modes of transmission from one generation to the next are not simultaneously estimable, that it is necessary to fix either the P's to 0 or the gammas and the etas to 0. But what the model does have is this very nice random intercept component separated for both the genetic and the environmental pieces. So these factors here are saying that there's a dose of genetic or environmental variation that influences every time point equally. These GC and EC parameters are constrained to be the same. And indeed, these GC and EC parameters could have been substituted with ones and estimated the variance of EC. Of course, back in the 1980s, we weren't so good about including explicit variance paths in the path diagrams, and this diagram is one of many such that lacks the formalities of specifying the residual variance components, etc. The residuals here are in fact specified as sort of the innovation variance, that is ES, specific to each occasion, and similarly GS is specific to each occasion. So I highly recommend you take a look at that paper, and not least because in addition to presenting this Markov model for discrete times, where we're assuming the entire sample's been measured sort of say at their 18th, 19th, 20th and 21st birthdays. But of course, the reality of longitudinal studies is difficult to get people to show up on their birthdays for testing. So he developed the model further for continuous time, and that is for a variable interval between the occasions, and he used differential equations for that specification. So here's a quick summary of those things, and it sort of ends with this question: what about cross-variable transmission? So far, everything has been with perfect fidelity. That is, the genes are causing the genes, the environments are causing the environments, the phenotypes are causing the phenotypes, and the head bone's connected to the neck bone and all the rest of it. So when you start thinking out of the box, such as a creative individual named Connor Dolan might do, Connor, here is that same model specified in a horizontal rather than a vertical transmission sort of way, traveling from time point 1 on the left-hand side to time point 4 on the right-hand side of the figure. And within each occasion, you can just about make out an ACE model. There's an A, C, and an E causing each of the rectangles that you see demarcating the observed measures in this study. So it's not too complicated in terms of observed measures. We do have multiple groups, the usual MZs and DZs, but we only have 8 variables measured per twin pair in this particular 4-occasion model. And here we got to think about, well, maybe it doesn't just work from environment to environment or phenotype to phenotype, but in particular, is it that my phenotype is influencing the environment on my environment on a subsequent occasion? So that type of specification is involves a transformation of this model. In fact, the paths are shown here on this initial slide, but they turn out, if you draw them a bit thicker, it's easier to see what we're talking about. In this case, we're looking at the phenotypes on one occasion causing that individual's environment on the subsequent occasion, and this process continues through time. What's further possible in this context, and also of substantive interest in certain respects, are the so-called beta paths. So these alpha paths are for self-niche selection, but it may be that a person can influence their co-twin's environment for the next occasion as well. And these are the beta paths drawn in the thicker arrows in this version of the diagram. And in the practical sessions, we're aiming to have some practice at fitting these various models to some observed data. So in conclusion, we've got simplex and Markov models that are very simple in principle. In behavior genetics applications, I think I've only seen first order, that is that there's no direct or no effect of time 1 on time 3 that does not pass through time 2. So this is strictly a first order Markov model. If time 1 had a sort of end run, skip out time 2, pathway directly to time 3, then we would be looking at a second order Markov model. These ones are what we generally call first order Markov models. Obviously, the Markovian process readily extends to the latent variables, to the A, C, and E in the twin model. And it is usefully, I think, implemented with twin sibling data to test hypotheses about niche selection and sibling interaction. And for future directions, the obvious thing to start thinking about is, okay, so many of the subjects in these studies have been genotyped. It's fairly straightforward to calculate polygenic scores for those individuals, and what kind of role might polygenic scores play in these time series models, and do they help us to discern direction of causation? And one such area of interest of mine and several of my colleagues, Dave Evans in particular, is Mendelian randomization, where we're looking at genetic effects and, say, an exposure and an outcome. And there's a great deal of development work in that area concerning the application of polygenic scores to time series data. And we can expect similar and further multivariate or network applications of this model. But I'm going to leave it there for now. Thank you for your attention.